Welcome back to the APSCC 2021 webinar series. I'm Christopher Slaughter, your MC for the series. Today, the subject is Optical and Quantum Communications, ready to launch. Joining us today, we have Rizwan Parvez from Maxar, who is the moderator for today's session. He's joined today by expert guests, including Rob Beddington from Spectral QT, Yohei Sato from JAXA, the Japanese Space Agency, and Rob Singh, who is the CTO of SpaceLink. Please take it away, if you please, Rizwan.
So good morning and afternoon and evening to our audience that have logged in today to watch our panel. And the panel today is focused on optical communication technologies. I'm Rizwan Parvez, part of Maxar and the business pursuit team for the US government civil space projects. But my background has included 5 years deep into the optical communications world at some startups so this is a bit of a passion topic for me. And just a little bit more background is my career has been based in space and communication systems for nearly 2 decades now. So happy to be invited to moderate this panel and be able to speak to our panelists about optical communications, quantum communications, a little bit of history, a little bit of current initiatives, and how all this will play into the future of the industry. So I'm actually going to use today's panel to take a little bit of a step back by actually getting into some more details on the history of this technology and a number of current initiatives that are currently underway to really provide a little more color to our industry on what's all too often probably glanced over in other forums or in other discussion panels where very ambitious projects are spoken about, and they just kind of assume that optical technologies and optical capabilities will just be there. The comment is, oh, we'll just have an optical link to solve that. Or how do you get around the bandwidth problems? Oh, we'll just put optical on there. The reality is that there are still steps to be taken in this industry for optical and adjacent optical technologies to reach the maturity that we are all pushing for to enable a lot of these ambitious projects that exist and will exist again in the future. So to be able to go into a little bit more of a deep dive in the history and the future of the technology, we have a panel here of essentially some high-level technical leadership from industry. I'll introduce them shortly so they can give a little bit of background about themselves and the organizations they work for. And I'll basically be kind of asking them throughout the next couple almost hour here about, what are the precursors that we should all be monitoring and supporting so that we can all see come to fruition the ambitious plans that are laid out by our industry and by a lot of our peers in this industry. To kind of start out with introductions, first, Rob Beddington from Spectral, a quantum communications company based in Singapore. Rob, if you could quickly introduce yourself and a little bit of background and what your company is up to.
Sure, thanks. So my background is in physics, and I a PhD in plasma analyzers for sounding rockets and satellites, and then after that I sort of moved into quantum instrumentation. I was at the National University of Singapore for quite a while, and as quantum communications became a bigger and bigger topic as the Chinese launched their Mesius mission, there was just more and more attention on this group at the university asking, can we buy some quantum payloads from you? And it became apparent that there was an appetite for a quantum comm startup, which is ultimately what we did. So in 2017, we started Spectral, and then we transitioned full-time in 2019 when we had the seed round funding. And so me and the team that was at NUS building the satellites there are now at Spectral commercializing the quantum comms technology from National University of Singapore.
Okay, and thank you. Next on our panel is Yohei Sato, from JAXA, who was part of the Japanese Data Relay System project. So Sato-san, can you please introduce yourself?
Yes, my name is Sato Yohei from JAXA Japan. My background is electronics, radiation physics, and satellite system. I have in charge in the Jdrs, Japanese Data Relay System projects. I have in charge the optical design and how to say English, transponder between light communication and RF communication. And I have in charge also the optical power amplifier. Is it okay?
Yes. Okay. Thank you.
So sorry, I'm not so familiar with English communication. So sorry.
No, you're fine. You're fine. Thank you for your attending today's panel. And Rob Singh of SpaceLink, a subsidiary of EOS, which is a group based out of Australia. So Rob, a little bit about you and SpaceLink.
Thanks, Rizwan. So I'm glad to be here. I think I'm Chief Technology Officer at SpaceLink, and recently with this venture and activity in the start of this year. My optical sort of background goes all the way back to my undergrad and grad work back up in Canada. We were looking at laser optically controlled RF devices. A little more about me was that I ended up coming back into the Silicon Valley Bay Area for quite a few years back and joining Space Systems Loral. So I was there for about 15 years running comm systems. Left the optical for a while and was steeped in the RF side. We've got a number of satellites that SSL's flying in orbit on the order of 90. It was fun to be able to touch and design the communication payloads for about 60 plus of them. Last few years was dealt then in with Maxar strategic initiatives. And with strategic initiatives, it was really a crossover, looking at what's happening 5G, looking at what's happening optical, how it can tie into to new applications that we can have in place. And that's where sort of my sort of shift and joining up with SpaceLink, as you mentioned, is hard focus right now on relay solutions. And we're really bridging between RF and optical and trying to find the right balance between those in the application that we hope to be quite disruptive.
Okay, and thank you, Rob. So I'm going to kind of right now take a little bit of a step back and provide a little bit of backdrop as to how optical technology is where it is today, specifically free space optical technology for aerospace efforts. So initial space efforts, at least far that I could track, really started to gain some steam, early steams back in the 90s. Mostly led by national space agencies, including JAXA. And you can kind of read a bunch of papers from industry, from photonics organizations, electronics organizations, aerospace organizations about what those efforts were. And we were talking about data links in what was then in the megabit per second, and that was viewed as an order of magnitude higher per link than anything that could have been achieved in RF at the time, using the frequencies that were common in satellite communications at that time. Apart from the national space agencies, in the commercial arena, probably an effort that took quite a bit of focus was Teledesic, one of the first players in the first generation of the ambitious mega constellations, which ultimately did not end up panning out, but Teledesic was an effort where a number of organizations and a number of industry players were looking to kind of find an initiative to really help propel optical communication technologies from those national space organizations into kind of the commercial arena. Now, while Teledesic didn't quite work out, at least within the US, another major initiative that came about that kind of got the industry culled back together to work towards a major project was the Transformational Satellite Communication System that the United States Air Force was working through, also known as TSAT, but not to be confused with TASAT of Germany, which is a prominent laser communications manufacturer. Now, back in the early 2000s, again, as momentum started building up a little bit in industry, ultimately that transformational satellite system was canceled due to a combinations of the technology readiness risk level just not being deemed sufficiently high, which was leading to a bunch of cost uncertainty elements as well. So based on kind of my research and my background into it, we kind of saw as an industry, even a global industry, kind of a retrenchment of optical initiatives to kind of stay within the research domain and programs sponsored again by the national space agencies. So from those kind of mid 2000s up until even now, it's the national space agencies that have continued on the optical communication march. So projects by NASA, European Space Agency, JAXA, DLR, et cetera, all worked together in cooperative manners behind the scenes to continue a steady ramp of communication capabilities. And as each project was launched, the data rates might have doubled. The distances reached may have gone from LEO to GEO out to lunar. And then with all those lessons learned, they kind of went back to GEO, bringing in some more capabilities. And today there's a lot of effort again back in the LEO domain with optical communications. But a lot of it's still sponsored by and being catalyzed by government projects. Now in the quantum domain, and we'll let Robert kind of go into this more, but it's also been very much a technology that has been promoted by research and academic institutions and national organizations, not so much the commercial drive to self-initiate and push something through. And maybe back in the optical comm domain, I mentioned that even today, it's primarily government-driven projects that are pushing the technology, doing the demonstrations with the technology. Perhaps the only exception that we at least know about publicly is, we know that SpaceX, with their current Starlink generation, appear to have optical ISL on board again, though we don't have any public kind of disclosures about how well they're working. We certainly hope them well because we want the industry to definitely move forward and optical to become more commonplace. But my kind of assessment is that we have yet to kind of see that qualified substantive proliferation of this technology, despite nearly, I'll count up easily a dozen different organizations, non-government organizations that are using venture money, commercial money, that are trying to really get this technology pushed into a little bit more of a proliferated regime and not just in the domain of the big national projects. So today, while we have some rather substantial initiatives underway, and these initiatives, at least relatively speaking substantial, are really, again, to try to help catalyze optical to kind of hit a step function to get into a higher level of commonality. Within the United States, we have efforts by DARPA and the Space Development Agency that are specifically designed to make optical a little more commonplace and a little more available in industry to be able to help fulfill a lot of these ambitious, robust, high bandwidth mesh networks. But the question is going to still remain. We're in May 2021 now. And will optical communications finally stop being viewed as what I commonly heard in a comical term as it's the perennial next generation technology. And no matter what generation you're in, optical will always be the next generation technology. It's always one step away. So I'm more optimistic than ever that, especially with a bunch of efforts and a bunch of on-orbit recent demonstrations, that that one step away is just getting a little smaller of a step before we see more proliferation. But we hope to get more out there. So again, what I just kind of spoke about for the last few minutes here was the backdrop that's very focused on optical communications. I'd like to first take a little bit of a sidestep here and go to Rob Beddington to talk about getting a little bit of backdrop on optical quantum communications and what sort of parallels that technology has run that kind of similarly follows what we saw in free space optical comm.
Sure, yeah.
Rob?
Yeah, so I mean, quantum communications in space is certainly a newer topic than conventional optical communications in space. But I guess the trajectory is fairly similar. And QKD itself is not a new thing. So the first QKD quantum key distribution experiments were back in the 80s, just in academic settings in laboratories, and they sort of continued through the 90s, finding new and different ways of communicating through the quantum states of light, and people sort of started talking about this in a space context probably start of the 2000s. There was some papers going out there from European and US groups, and the US really started to fund development of satellite QKD projects back at that time for the academic research. But then the funding then got cut in some funding review in the US, and sort of quantum comms activity generally stopped for a while, or was at least greatly attenuated in the US. And then the sort of focus shifted to Europe for a bit, and there was a few sort of European Space Agency proposals for quantum communications missions, but again, none of those really got much traction. And it was really sort of in the last 5 to 10 years in Asia where satellite quantum comms really became a thing. So the group I was at the National University of Singapore, we launched the sort of the first quantum light source, a very, very simple device making correlated pairs of photons in the CubeSat. Back in sort of 2016, the Japanese did some experiments with very weak light states being sent from microsatellites to the Earth, and then of course the Chinese launched an amazing, really comprehensive quantum mission that basically proved that all of these quantum communications things that we've been talking about were possible, and they are currently the only country or the only group that's doing quantum communications in space right now. There's 2 quantum satellites in orbit right now. Well, 3, I guess. One from the Chinese, and then 2 from Spectral and the Singapore National University groups. But yeah, it's the Chinese satellite that's really in the lead. That's all sort of academic stuff right now.
So in terms of startups, and in terms of startups, they're founded to solve a problem. So could you give a little bit of background onto what is the problem that Spectral is solving, and how does the technology that QKD solve it?
Sure. So why are we bothering with this whole quantum thing in the first place? What was the attraction? Quantum communications, at least what everyone's doing right now, is not really about communicating information like we're doing in this call. It's really only about sharing secret bits. So it's about generating strings of random numbers that are shared privately between 2 ends of a connection. So the whole point of this is just to establish encryption keys in a very secret way. And the reason this has become popular all of a sudden is, well, firstly, because it's been made possible by the optical comms techniques, which you guys have been developing, and we can just sort of leverage on those developments. But secondly, the development in quantum computing has also really ramped up, and quantum computing is threatening the encryption systems that we use on a daily basis for securing, for example, this call, and for any sort of internet transactions. These sorts of mathematical-based encryption using public-private key technologies, the security underlying this will be invalidated by future quantum computers, and quantum key distribution, this way of generating encryption keys using these very weak light states, this is invulnerable to quantum computing attacks and to any sort of computational attacks. So basically, we, as a society, we need to step up our game when it comes to encryption and security. And QKD at the moment is one of the sort of the most promising ways of doing this.
Okay. And then kind of who do you think are your target customers? Who are the organizations that you guys are speaking to on a regular basis or are showing the most interest in watching this technology mature and then ultimately implementing it?
Yeah, so it's anyone who really values the security of their data over the long term. So if you're just worried about sort of your credit card transactions, then that has a sort of fairly short time over which you're worried about that security. Once a credit card expires, then it's not a problem. But if you have sort of long-term data security requirements, then we don't know when quantum computers are coming. So we need to be prepared in advance for that. So these are groups like telcos and data centers and sort of big financial institutions, multinational companies who have sites all around the world, and they don't want sort of foreign governments and competitors tapping the communication between these sites. All of these sort of big organizations with sensitive backbone networks are really the people who are showing the first sort of interest in quantum key distribution.
Okay. All right. Thank you. So turning now back to kind of in orbit projects with a little bit of a longer history to them. So Sato-san, can you kind of provide a little bit of brief history on Japanese space glacial communication activities, stretching back from the 90s all the way to what's going on right now?
Yes, Japanese light communication history is studied at 1990s. And the first mission is PTS-6, Engineering Test Satellite Series, JAXA, and previous organization of JAXA named as NASDA, NASDA, developed ETS-6. That Japanese first light communication mission. The data rate is 1 megabps. After that, next Japanese optical telecommunication mission is OISET. It's launched at 2005. The data rate is 5 megabps. After that, we have considering next light communication mission, and the Lucas had been started the development at I forget around 2014. And last year, Lucas was launched. The data rate is 1.8 gigabps. Data user rate. A simple rate is 2.4 gigabps. And we are discussing about next future plan and the roadmap. Is it okay?
Mm-hmm. So basically, every increment you guys were doing, and you were doing kind of from megabits to gigabits to now, yes. I think the next major project in Japan is 10 gigabit per second from GEO. So there's an incremental order of magnitude step every project that you guys work on.
Yes, that's right.
Okay, so Jdrs you mentioned was launched very recently. Can you give us a status of that optical payload and experiments being run?
The orbit is geostationary orbit, and the user satellite is GEO satellite. It will be launched as this Japanese fiscal year. So sorry, it's not so clear. It means the next month.
Okay.
It will be launched, named as APSCC 3.
Yeah. And then what were some technical challenges experienced during JDRS program and the payload development? Do you have any examples of particular areas that were challenging?
There were very many technical challenges. The biggest one is acquisition and tracking system. The last target of the tracking accuracy is less than 10 microradian. So how to make this kind of so accurate acquisition and tracking system? It's very difficult. It was very difficult.
Yeah, I think that size microradian from geostationary orbit is only like a football field size, almost pointing on the footprint on the ground. So,
yeah.
Okay. So, Rob, kind of turning to the future and implementations. So your parent company, EOS, acquired the RF spectrum rights from Odyssey, which was a previous startup that had ambitions to also be a relay company. But what will make SpaceLink different than how Odyssey approached the relay market, and what technologies are you guys looking at that may be different than what the kind of previous organization tried to implement?
It's actually interesting, Rizwan. There's a couple of points over here. It's you're right that EOS successfully acquired Odyssey's rights and spectrum rights, and Odyssey initially under their objective was forming, as you said, a startup always has a problem they're solving, which was basically LEO to MEO relay comms back to ground in the RF domain, and hence the ITU FCC spectrum rights. With EOS as our parent company, and then us establishing SpaceLink in the US, the intent was to continue that objective of basically what can we fly in MEO orbit that gives us 100% line of sight access to all the LEOs above 350 kilometers. And because the LEO missions are very mission directed in terms of heavy data rate, what can we do to help backhaul or provide a data stream back off of those assets? The conversation's been interesting because you talk about the evolution and what's different with SpaceLink versus Odyssey, or how it's moving is, I think the most fundamental has been technology movement and what we've seen in the last, particularly even in the last 2 years and the last 5 years in the optical domain for comms. So where we were going in initially of thinking of, hey, this could be an RF phase that then migrates to an optical. I can say now we've actually done a fairly hard pivot, and we've now ended up with an improved architecture that basically is an optical RF hybrid architecture. So to provide potential LEO clients with either an RF or an optical link to bring data back from those clients.
And what is it about MEO that attracts SpaceLink to go after? It's certainly not as common as the proliferated LEO that's going on right now, nor traditional geocom environments and industries. So why MEO? And how does that radiation element of MEO impact how you guys are proceeding with your design and considerations for reliability and things of that nature?
Yeah, and it's a great question. I think what's ended up happening is, first of all, I'll talk about the positive side. Was the MEO we purposely chose running at our license and our spectrum rights that we had originally is operating around 14,000 kilometers. Basically, with 3 satellites in our orbit, we actually have what I was describing as 100% line of sight access to the LEOs. So it helps both in data and tasking and access. If we end up with more satellites, it just gives us more capacity and more capability. But that MEO orbit gives us this this view of accessing the clients. The second part, though, is on the flip side. Though MEO is not necessarily an easy environment. It's tougher than LEO in terms of radiation. It is a little tougher than geo. A lot of us have worked in the geo environment, so there is a step up there, but not impossible. You know that there are a number of applications that are operating in MEO, including GPS systems, and so what we are intending to put in place, I think is well within the capability, and we're just focused really hard on, there's a radiation side to that. There's how do we get to the MEO orbit, but the capability of having a certain limited number of assets to be able to provide this connectivity to the LEO marketplace has really been the focus and the drive.
And you mentioned this hybrid RF optical implementation. What about the links to the ground? Are those also going to be hybrid of RF and optical, or predominantly RF, or any optical at all?
No, so I think we're selectively sort of picking and choosing where we're applying sort of advances in technology and giving some more time where we want to see some more maturity. So certainly the ISL or our satellite to satellite links are all optical. Satellite to client are a mix of optical and RF, and our satellites from MEO to ground are VQ band RF. And it's that combination that we're finding is providing us sort of the right capacity and capability mix that we need.
Right, thanks. So Rob Beddington, kind of just going on that sort of like adjacent technology capabilities, you know, that RF optical that Rob was talking about. Are there any kind of rival technologies or adjacent technologies then in your domain that could solve the problems you're solving in a similar manner? Are there any benefits of that or any deficiency of any rival technology?
Sure, yeah. So the comparison which is usually made, or the options people usually consider, would be between QKD and PQC. So QKD is quantum key distribution. That's what we're doing at Spectral. This is the weak light signals to make encryption keys. The alternative, which is usually considered, is PQC, so post-quantum cryptography. So this is doing encryption over mathematical functions that are sort of similar to how we do encryption today, but in ways that are considered, or at least hoped to be, resistant against quantum computers. So these are sort of very, very different things, but trying to achieve something similar. PQC wouldn't involve satellites or any other sort of extra infrastructure particularly. It would just be a sort of direct replacement for public key cryptography. But the problem which everyone's trying to assess is how much can you trust that? Like when we set up the public key infrastructure that we use now, we assumed it was also going to be secure forever because we didn't sort of see quantum computers coming, or we didn't appreciate that they would be able to solve problems which the conventional computers couldn't. And right now it's very difficult to sort of put a finger on what problems quantum computers won't be able to solve when we don't really know what quantum computers will look like and how they'll operate and what other sort of technologies come up. So there's certainly both PQC and QKD will be used and are being used as we approach the oncoming of quantum computers. And really, I think it depends how valuable your data is, how worried you are about security as to which option you turn to. So the most, I guess, the most paranoid, or the people with the biggest security requirements will turn to QKD because there are clear proofs there of how the laws of physics are protecting you. Sometimes people describe it that way. Whereas with PQC, you're taking more of a gamble as to whether quantum computers will or will not be able to crack them. That's the main sort of...
So looking years or decades down the line, do you expect QKD or such security aspects to be for certain niche applications or high security applications, or do you kind of see it proliferating to every single user, every single satellite system needing to have that sort of security element, so implemented in its architecture?
Yeah. So I mean, realistically, it's not going to be everywhere. I wouldn't think, not at least in 10 years' time. It's just too much extra infrastructure required. But if enough effort is put into it, then these things. Like we thought, sort of like fiber optics to every home was seemed like a long shot for a while, and now, at least in Singapore, everyone has fiber optics. And as long as you have fiber optics, then you can do you can do QKD. So potentially in Singapore, everyone could do QKD between all their houses, and then once sort of chip scale QKD systems are available for mobile phones, then you could do that when you connect to the ATM. You could do a QKD transaction between your phone and the ATM, and these sorts of things have been developed. So it's possible. It depends how this PQC versus QKD trade-off continues. But I mean, really, right now is an opportunity to rethink how we do security, how we do encryption. So before, encryption's always been that thing which has been bolted on when someone realizes there's a problem. So most of the sort of internet protocols, when the internet first came out, they sort of sent everything in plain text, or they just had very, very simple password and authentication systems. But as sort of nefarious actors joined the internet, as hackers came along, then people had to start bolting on, like, oh, okay, we'll encrypt this, and we'll put some keys around this, we'll have some public key exchange going on here. And encryption's always been sort of an afterthought. Now we have this sort of real opportunity to sort of, from the ground up, build systems that are inherently secure, where it's not an afterthought. And QKD has a part to play in this. So QKD is about having an extra layer of infrastructure for distributing the keys separate from where the data is flowing, to allow this sort of thing. And I guess the other reason why people are investing in QKD, even though it seems like, well, this is an expensive alternative to just doing some mathematical crypto, the other reason is because it has applications beyond security. So in the far future, so I don't know, 20, 30, 40, 50 years, then the quantum communications becomes more about networking quantum computers, and less about security. Well, the security bit is still there, but we can use this capability for networking quantum computers in a way that classical networking really cannot compete. So particularly in Europe, lots of the sort of QKD initiatives are driven by this quantum information long-term proposition, where, say, if we can share entanglement between quantum computers, then we can have vastly more powerful quantum computers. The same as like back in the 40s and 50s when they first started building computers. We started with that, and then by networking them all, we can have the internet. Now in 2020, where we have all these video calls, it's the same sort of proposition. Right? The quantum computers we build today, they seem pretty neat, but just imagine 50, 60 years into the future, if they can be networked in this sort of native medium, it's sort of the possibilities are really sort of beyond our imagination almost.
So is it fair to say that let's assume that optical communications can implement it, and we start seeing it build out on satellite systems, ground systems, that really that's a core infrastructure that QKD can harness as well, right? Yeah.
I mean, so we kind of leverage all the work that you guys do on making optical links, and we just send our quantum signals down those same optical links. So if there's optical links on satellites, then we can try and use those, or at least reuse that technology and have an adjacent unit that's doing quantum keys. Absolutely, the two go very much hand in hand. Okay. But they don't have to, but they do complement each other well.
I guess there's an economics benefit that you can leverage on top of.
Yeah, for sure.
So Sato-san, going back to kind of the projects that exist in JDRS to be specific, can you provide some more understanding of the capabilities of JDRS? What are the data rates that you're either achieving right now or will plan to achieve when you launch a LEO satellite also? And then can you also describe the transmission, the angles, the microradian angles you guys talked about, and to be able to do that, how was the pointing achieved?
Yes, the Lux data rate is 1.8 gigabps. It's a service link, returning come to LEO satellite to ground station via GEO satellite. And forwarding, it means from ground station to user satellite via GEO satellite is 50 megabps. And you mean the vertical transmission angle?
Yeah, so that's uplink to ground. What will be achieved GEO to LEO satellite when you have intersatellite demonstration in a few months?
Data rate is last answer, and pointing accuracy is last point accuracy is around less than 10 microradian.
Okay.
Before the acquisition, the pointing accuracy, open pointing accuracy is 0.2 degree is needed.
0.2
degree.
Okay.
That's
So-
before the acquisition.
Okay, so if the LEO satellite can do 0.2 degree accuracy, then the optical terminal that JDRS designed can do the search acquisition and closed loop attachment, right?
Yes.
Okay.
Is it this enough answer?
Yeah, no, so then the final question is, what is the size of the optical
size.
terminal that will go on the LEO satellite?
That's I haven't known. Size is around GEO satellite terminal is around 1 meter and 70 centimeter and 50 centimeter, around this size.
Okay.
And the LEO satellite terminal is 90 centimeter and 60 centimeter and also 60 centimeter.
Okay. So these are not these are not CubeSat terminals then, correct?
It's a little bit different to load on the CubeSat.
Yeah.
Currently, the size is a little bit big because the duration of development is too short. It's coming from the requirement from Japanese government. So we have selected the design. The size is big, but it can be realized in the short-term development.
Okay. So Rob, going back to the future, the regulatory environment that you guys have to work in the RF domain and the lack of it in the optical domain, how much of that comes into play when you guys are designing out your architecture? And do you foresee the regulatory agencies eventually trying to figure out a way to do something in the optical domain, or do you feel like they'll stay hands off?
I think obviously we're working very closely with the regulatory side because of the RF aspect of our architecture and what's in play. From an architecting standpoint, I usually don't hesitate from that because we're coming in with knowledge as to how to deal with it. But I think we ended up with an interesting factor, though, that when we think of our clients as LEO and LEO customers, and a number of them as emerging new space, that hurdle of regulatory planning application by trying to put an supporting an RF link, I think is a factor. And so, it is quite enticing to say, could we be in the optical domain? Could we actually just focus on what we need to put onto our system and avoid sort of the regulatory process that's involved? But I think it does have a factor to a number of clients that we were working with and we're looking to streamline that. So while we're having a combination of RF and optical, it's interesting to see how we can work with both. So I think optical will be back into, is there a regulatory body at some point that has to step in? You know, I find ITU, FCC implementation for what we're dealing with is really on interference and helping to coordinate operations in that sort of a more contested or conflicted environment. So again, there's some uniqueness on the optical side that helps sort of say that we're not in that shared space anymore. You know, the beam sizes are of a certain size, the way we're tracking, the way we're implementing. And so at this stage, I don't see a regulatory need for stepping in at this point. We do actually have some with aircraft, ground to air, ground to spacecraft activity, but again, our focus has been in space to space, and so falls in that non-regulated area.
Yeah, just speaking from a past life, most of the regulatory elements we dealt with were human safety, eye safety related sort of things, or being able to showcase why it's not a burning hazard, anything of that nature, which are different wavelengths, different frequencies, different power density levels. Doesn't really apply to the communication side of things. So other kind of trends you guys are looking at from an industry perspective, you know, one of the things that I kind of note is geodistance relays today are, you know, in the 1 to 2 gigabit per second domain for things that have either been launched or are planned to be launched in the next year or so. In the LEO world, you know, 1 to 10 gigabit per second ISL link seems to be where today's technology is, or where the majority of current builds are being focused on. You know, but we see kind of in some future forecast of mesh networks that industry wants or is expecting much higher data rate and data bandwidths in the tens of gigabits per second, if not hundreds of gigabits per second. So from your perspective at SpaceLink, are you guys waiting to see how others in industry kind of achieve those higher data rates, or do you guys see yourselves amongst the leaders of trailblazing to be able to get to those higher data links sooner rather than later?
Rizwan, it was a loaded question, so I think consider for SpaceLink as a trailblazer. But I think of it this way: is, you know, innovation in any industry and stuff. A lot of times you can actually lean on hard to adjacent areas and what's been developed. So obviously, optical, terrestrial optical, and where things are moving with, you know, whether we're running with on-off keying or we're trying to look at coherent implementation of optical modem and receivers. Where we think that it may go in terms of telescope, optical size, power. All these are factors we've been looking at pretty closely to try to make sure that we have a design that is state of the art as it is today. But I almost go back to your comment at the start of our session where you're talking about the different agencies, and you were mentioning JAXA and then tied in with you know, NASA, ESA. I do find that in this last round with you mentioned DARPA, SDA, sort of seeing the proliferated LEO and the push for interoperability on the optical side, that the industry is really, from my perspective, looking at, has really stepped up. And so there's a lot of work being done very similarly, trying to move to that common standard. But whether the common standard is achieved, certainly there's a lot of focus on what's the next step, what's the roadmap, and how we move through. And so I think that's a key factor in trailblazing almost is having some part of a crystal ball that you have in front of you, and then saying, okay, how can I future-proof my system, or do I know what's happening next so that I'm in good position to capitalize on tremendous work that people are doing in all these adjacent industries. I think that's sort of the key that we have when we're looking at what is happening in the future, what can happen in the future.
Thanks. And Rob Bennington, as far as kind of next steps for quantum comms, you know, we've seen projects from universities and academics, and you guys have done your own kind of working with the university's ecosystem. Are you guys planning to do any more launches in the near future for technology demonstrators, or are you guys now in a state where operational implementation is what you're looking for? And, you know, if it is still a technology demonstrator phase, you know, what more needs to be proved in order for industry to say, yes, we're at the right level of technology readiness for industry adoption?
The leaders here are really the Chinese, and so they've written some papers about how their system is being used sort of operationally. I think probably just for a few smaller users. So I think there probably are some people that are actually using satellite QKD right now, not within Spectral, but globally. Our next mission we think of more as a sort of service demonstration. For sort of early adopters, people that want to test drive QKD, they will be able to test what it's like to have this extra encryption layer on some of their communications, but we wouldn't really imagine them using it sort of operationally, not with the first satellite, or at least not for the first year or so of operations. So I think for individual companies, there's some technology bits to be proven, some bits to work out, but globally, these problems have been solved, and if there was a sort of sudden massive demand for these, then we could roll them out even quicker. But we expect this to happen, you know, gradually as quantum computing threat sort of nibbles more and more at people's conscience, and sort of concerns about data security increase, and we'll be there to match it with the capabilities we can offer.
Okay, thanks. So Sato-san, some questions about kind of next generation systems from the Japanese technology side. So you said JDRS is 1.8 gigabit per second. I've read that ETS-9, which is Japan's next project, is going to be 10 gigabit per second for GeoLink. But then future systems want to do even more data rates, 100 gigabit per second, maybe even one day terabit per second. Is the plan for those systems to just be able to do more complex modulation, or is it more wavelengths, or a combination? What is the roadmap to be able to achieve higher data rates than what has been demonstrated today?
That's a difficult question. We are considering about next target data rate and functions. A function means, for example, multi-data rate and so on. We also discuss about how to achieve that goal. WDM is also one of our candidates.
And for WDM, how many channels is expected?
Sorry, currently it's under discussing. It depends on the next data rate target, I think.
Okay. And then for JDRS communications to the ground, how many ground stations do you guys currently have that you are testing with?
We have only one ground station located in western side in Japan.
All right, so Rob, for SpaceLink, kind of tying back into Rob Beddington's industry, is there any plans on monitoring the QKD industry and trying to figure out, can you guys roll in this level of security layer into your architectures in the future?
Absolutely. Just looking at, or just hearing sort of how Robert's describing where things are. I put that in sort of the adjacent. Actually, we're actually in a phase right now. We're really exploring hard for the architecture that provides the base sort of relay, where other value proposition capability may come into play. The traditional needs for encryption are very high, so in the standard methods of implementation. So that's certainly there. But exploring how we could be utilizing QPD just becomes another value proposition. So there is interest in there. I put it towards our road mapping activity, but certainly active to see what we can do there. A second part, like I say, is it's anytime we've got optical systems, it's interesting to see what others have been using to gain value out of it. We're seeing a lot of work also in alternate precision navigation timing and distribution for GPS denied services. So there's a number of other aspects that become sort of even give it an enhanced value to then just the traditional data relay system.
And Rob, I think kind of getting back, wrapping up with you here. Is the technology, you said probably a couple more steps or before it's like fully operational, but do you see industry fully engaged with you guys, and are they eager and pushing you guys to move this to fruition so that they can implement it as soon as possible, or is it kind of the trend of people waiting to see if this becomes a big enough problem and will then move on it? What's kind of the customer trending that you're seeing?
Yeah, so I'd say that the only place where that seems to be happening really strongly is China. I mean, that's maybe the Chinese government pushing their technology on their companies. I'm not quite sure. Right now, it's people like the European Space Agency that are really pushing this development to sort of build the infrastructure out, and then industry can work with that infrastructure which ESA puts in place. There are certainly lots of curious companies. I mean, I think so. The sort of things Rob Singh was saying there is sort of like, yeah, this is something that's on our roadmaps. We're thinking about this. It's definitely interesting. We're not quite sure how it fits in just yet. There's certainly a lot of companies at that stage. But yeah, I think with the continued pushing from ESA and equivalent agencies, then it will really get out there.
You're almost waiting for somebody to help put up the towers first, and once those towers are up, the implementation of augmented capabilities is an easier thing to push out.
Yeah, and the Chinese government and ESA and other people are putting up those towers, so yeah, let's see how that goes.
So Sato-san, kind of final question for you. JAXA has a lot of experience now with in-orbit demonstrations and lessons learned. Is there a way for industry to be able to work with JAXA and be able to gain access to these lessons and get advice from JAXA on design reviews and design implementation?
Oh, it's a little bit difficult question. I cannot answer in official, so how to say. Anyway, you can contact the JAXA's inquiry counter for public sections and international department section. So you can access them. And also JAXA's English version website has an inquiry form. So you can access these contacts.
Thank you. And then Rob, kind of wrapping up with you. Kind of two questions. One is the U.S. government is, as an effort that they just released a preliminary release just earlier this week about looking for the commercial industry to implement a commercial relay system to ultimately transition off government-owned Jdrs systems. Going back to kind of your MEO architecture, is that fundamentally harder to be able to relay connect into because the data the relative speeds are faster than a relative speed to GEO, or more complex pointing acquisitions?
For us, actually, no. When we looked at this, both you're saying for the optical and for the RF, replacing Tdrs RF systems, and then also the potential of migrating or switching over to optical. For the client users and the terminal capabilities that are being designed into the LEO application, the LEO to MEO is ends up being well within their capability from that side. Now, obviously, we have the link and the link challenge, but I think the link challenge also in the MEO is in a better situation than it would be going to GEO. So there's a couple benefits on both sides that non-trivial, but and need to be worked. But I think we're in promising position here to say why this is in this we expect to be the transition. Relay systems will move to this, as we put it, an RF optical hybrid type solution, and MEO does provide a benefit to do that.
Yeah. And my final point, or my final question is, there's a lot of talk or industry chatter about how many communication mega constellations will survive at the end of the day. What's your perspective on relay constellations? Will the industry grow sufficiently so that more than one commercial relay player will be able to thrive? Or do you think it'll come down to one team kind of becoming the commercial player here?
No, I think the anticipated growth, if we're looking at which data are we trying to move, and if you're taking a clue from the LEO market of what is being put into place, there's been there's a proliferation there of applications in sort of the Earth observation, whether it's SAR spectroscopy, if it's electro-optic imaging, but the imaging need and the need for the turnaround time for that data, and also the amount of that data in terms of throughput requirements, I think we see easily as growing, and so there's room for multiples in there to support, and we certainly with SpaceLink's activity hope to be one of the first in place to realize this and make this all happen.
Okay. So yeah, thank you. And so that kind of wraps up kind of the questions I had for the team here. We wanted to kind of walk through a little bit of the history of where optical comm came from. Sato-san at JAXA was able to talk a little bit about, current implementations and in-orbit experiments that they've run. Rob Beddington chatting about adjacent applications that can build upon the optical comm architecture and infrastructure once it gets built out. And then, of course, we're all cheering here for Rob to be the person that builds out that architecture for everything to kind of wrap in together here with. So that's it that I had here. I want to again thank our panelists for joining me, and we'll see if we have any Q&A to answer. Thank you.
Thank you very much for that, Rizwan. Thank you, Rob, and thank you, Rob, and thank you very much, Sato-san. Pleasure to have your insights and inputs into the optical and quantum communications segment of the satellite industry. A pleasure to have you all today. Please do join us next week for the next session in our ongoing webinar series. If you want to know what's coming up, you can just go to the website at apsccsat.com, www.apsccsat.com. We've got on that page, that's where you register, and that's where you should be watching this today. There is also a tab that will give you the upcoming schedule and topics that we're looking for. We're working a little bit in advance, but there are changes that take place from week to week. So please do have a look and find out what the upcoming events are. Next week, we return to our operators series. This time we're looking back at regional operators. Joining us will be Virgil Labrador. He'll be the moderator for that particular session. But joining us as panelists will be Christian Patero from Pacific. We'll also have Pak Adi from PSN and Daniel Kim from KTSat. So pretty much a pretty wide gathering of regional operators to talk about issues they're facing here in the Asia Pacific region. Please do join us for that and spread the word. Cheers.